All right, welcome back. You're going to want to buckle up for this one because today we're diving into a theoretical paper that sounds like it was ripped straight out of science fiction. The big idea? A framework for turning plain old water into an interactive, programmable medium. It's called the Hydroholographic Cooperative Field. Yeah, it's a mouthful, but the name actually tells you everything. Hydro is for water, obviously. Holographic means the information is stored everywhere, not just in one spot. And cooperative field means it's a shared space for interaction. Seriously, this could totally change how we think about the stuff that covers most of our planet. So the whole paper really kicks off with this one simple but kind of mind-blowing question. Can we actually program water? And look, we're not talking about just making it flow through a pipe. We're talking about encoding stable, repeatable information into the liquid itself. To even get our heads around that question, we have to completely shift how we see water. We usually think of it as, well, a passive medium, right? It just carries stuff, it lets us sense things like temperature. But this HHCF framework is proposing a totally different view. What if water could be an active medium, a canvas for holding information, maybe even a tool for us to cooperate through? Okay, so if we're going to treat water like a new kind of computer, how do you write the code? Well, like with any new form of creation, you first need a language. So that's step one, figuring out what in the world a language for water would even look like. And the basic building block of this language is something the paper calls a motif. I love the analogy here. Just think of a motif as a single letter in an alphabet. It's a specific pattern that you can create over and over again in the water, like a little standing wave or a tiny vortex. The key is that it's recognizable. It's a thing. And this slide gives you a great idea of what the alphabet starter pack might look like. This is a basic motif library from the paper. So you have W1, which is this grid of waves. W4 is the quiet state, which is basically just a stable patch of stillness. The absence of a pattern is itself a pattern. And then you've got W5, a pair of little whirlpools. Now, these aren't just random ripples. They're distinct letters, and each one has a unique topological signature. That's just a fancy way of saying they have a core shape, like a fingerprint that software can identify no matter how much the water around it is jiggling. All right, so we've got our alphabet. Sounds easy enough, right? Create a few motifs, and we're good to go. Well, not so fast. That brings us to the single biggest problem in this whole idea. How do you keep those patterns from just disappearing? And this is the real kicker. Water is chaotic. It's messy. You can create the most beautiful, perfect little pattern, but give it a fraction of a second, and turbulence, heat, tiny vibrations, they'll all just tear it apart. It's a problem called decoherence. I mean, how are you supposed to write a sentence if your letters literally melt away the moment you form them? So the solution they propose is this really elegant 5-step control loop. It's a cycle that's always running. First, a writer, maybe using sound waves, creates a pattern in the water. Then a reader, like an overhead camera, watches it. A decoder, that's the software, identifies the pattern and checks if it's starting to fall apart. And then, this is the magic trick, the welder actively pushes the water to correct the pattern and keep it stable. And this loop just runs over and over, constantly fighting back against that natural chaos. Let's just zoom in on that last step for a second, the welder. The paper uses this fantastic analogy. It's like an always-on maintenance crew for your water pattern. And this idea is so much bigger than just water. It's a form of active error correction. It's the same fundamental concept that keeps information stable in everything from your Wi-Fi signal to the ridiculously fragile world of quantum computing. It's all about using information to fight back against chaos. Okay, this all sounds amazing in theory, a maintenance crew for water patterns, but how do you actually prove it's working? How do you know it's not just wishful thinking? Well, that brings us to what I think is the most important part of the whole paper, the break-even test. This is the fundamental scientific question, right? The authors aren't just making a cool claim. They're proposing a super rigorous, data-driven way to test it. How do we know for sure if this whole welding system is actually doing anything useful? And the answer is this beautifully simple idea called welding break-even. This is it. This is the single pass-fail test for the entire framework. And the idea is just so straightforward. For this to be a success, a pattern that you are welding has to last demonstrably longer than the exact same pattern if you just left it alone to decay. This slide lays out the experiment perfectly. It's a straight-up head-to-head competition. On one side, you have free evolution. You make your pattern, you start a stopwatch, and you measure how long it takes to fall apart. Let's call that lifetime T-free. Then, on the other side, you do the exact same thing, create the exact same tarn, but this time you switch on the welder. You measure that lifetime, and we'll call it T-weld. And that's the whole ballgame. The success of this entire project, at least for now, boils down to this one simple inequality. If the lifetime with the welding is greater than the lifetime without it, you achieved break even. You have proven scientifically that you can stabilize information in a chaotic mess. A wild sci-fi idea suddenly becomes a real, provable result. And what's so great about this test is how well designed it is. First off, it makes a really wild idea scientifically falsifiable. That's just a fancy way of saying it can be proven wrong, which is what real science is all about. Second, it's ungameable. The paper says you have to use the same energy budget for both sides, so you can't just cheat by blasting the welded system with way more power. And maybe the best part, it's designed so you could do it with pretty simple lab equipment. This isn't some billion-dollar experiment, it's accessible science. So, let's just imagine for a minute that they do it. They run the test, and T-weld is consistently greater than T-free. What happens then? What kind of world does that unlock? Well, this is where the paper gets really visionary. The possibilities they dream up are just fascinating. You could use it for an embodied learning, where you physically interact with the water to learn a task, and you get this immediate tactile feedback. Or get this, multi-agent coordination. Imagine two people having to work together to stabilize a really complex pattern in the same pool of water. It could even become a totally new kind of analog computer, a physical testbed for studying complex systems in a way you can actually see and touch. I wanted to share this direct quote because it just perfectly captures the ambition here. If yes, water becomes a shared substrate for measurable cooperation, embodied learning tasks, and physical analog testbeds. The whole point is to turn water from just stuff into something functional, interactive, and shared. So after going through all that, from the big idea to the nitty-gritty test, let's wrap this up. What's the one thing you should really take away from this entire framework? If you remember just one thing from all this, make it this. The real breakthrough here, whether it ultimately works in water or not, is the general idea of stabilizing information in a chaotic medium using a smart, closed-loop controller. That writer-reader-decoder-welder loop, that's a powerful concept that you could apply to countless other noisy, messy systems, way beyond this one experiment. And really, that's where we'll leave it. Yes, this is still a theoretical framework, but that elegant break-even test makes it a real, tangible, testable idea. And it leaves us with this final, really fun question to think about. If this actually works, if we could truly program water, what in the world would you build with a liquid computer?